This lecture is about the syntagmatic relation discovery and mutual information. In this lecture, we are going to continue discussing syntagmatic relation discovery. In particular, we're going to talk about another concept in information theory called mutual information and how it can be used to discover syntagmatic relations. Before, we talked about a problem of conditional entropy, and that is the conditional entropy computed on different pairs of words is not really comparable. So that makes it hard to discover strong syntagmatic relations globally from a corpus. So now we are going to introduce mutual information, which is another concept in information theory that allows us to, in some sense, normalize the conditional entropy to make it more comparable across different pairs. In particular, mutual information, denoted by I of x and y, measures the entropy reduction of x obtained from knowing y. More specifically, the question we are interested in here is how much reduction in the entropy of x can we obtain by knowing y? So mathematically, it can be defined as the difference between the original entropy of x and the conditional entropy of x given y. And you might see here, you can see here, it can also be defined as the reduction of entropy of y because of knowing x. Now, normally the two conditional entropes, h of x given y and h of y given x, are not equal. But interestingly, the reduction of entropy by knowing one of them is actually equal. So this quantity is called a mutual information, denoted by I here. And this function has some interesting properties. First, it's also non-negative. This is easy to understand because the original entropy is always not going to be lower than the possibly reduced conditional entropy. In other words, the conditional entropy would never exceed the original entropy. Knowing some information can always help us potentially, but won't hurt us in predicting x. The second property is that it's symmetric. While conditional entropy is not symmetric, mutual information is. The third property is that it reaches its minimum zero if and only if the two random variables are completely independent. That means knowing one of them doesn't tell us anything about the other. And this last property can be verified by simply looking at the equation above. And it reaches zero if and only if the conditional entropy of x given y is exactly the same as the original entropy of x. So that means knowing y did not help at all. And that's when x and y are completely independent. Now, when we fix x to rank different y's using conditional entropy, would give the same order as ranking based on mutual information. Because in the function here, h of x is fixed because x is fixed. So ranking based on mutual information is exactly the same as ranking based on the conditional entropy of x given y. But the mutual information allows us to compare different pairs of x and y. So that's why mutual information is more general and in general more useful. So let's examine some intuition of using mutual information for syntagmatic relation mining. Now, the question we ask for syntactic relation mining is whenever eats occurs, what other words also tend to occur? So this question can be framed as a mutual information question. And that is, which words have high mutual information with eats? So we're going to compute the mutual information between eats and other words. And if we do that, and it's basically based on the same intuition as in conditional entropy, we will see that words that are strongly associated with eats will tend to have high mutual information, whereas words that are not related will have lower mutual information. So this, I give some example here. The mutual information between eats and meat, which is the same as between meats and eats because mutual information is symmetric. is expected to be higher than the mutual information between its and the, because knowing the doesn't really help us predict its. Similarly, knowing its doesn't help us predicting the as well. And you also can easily see that the mutual information between a word and itself is the largest, which is equal to the the entropy of this word. Right? So because in this case the reduction is maximum, because knowing one would allow us to predict the other completely. So the conditional entropy is 0. Therefore, the mutual information reaches its maximum. It's going to be larger than or equal to the mutual information between its and any other word. In other words, picking any other word and compute the mutual information between its and that word, you want to get any mutual information larger than the mutual information between its and itself. So now let's think about how to compute the mutual information. Now, in order to do that, we often use a different form of mutual information, and we can mathematically rewrite the mutual information into the form shown on this slide, where we essentially see a formula that computes what's called a KL divergence or Kullback-Leibler divergence. This is another term in information theory. It measures the divergence between two distributions. Now, if you look at the formula, it's also sum over many combinations of different values of the two random variables. But inside the sum, mainly we are doing a comparison between two joint distributions. The numerator has the joint actual observed joint distribution of the two random variables. The bottom part, the denominator, can be interpreted as the expected joint distribution of the two random variables if they were independent. Because when two random variables are independent, their joint distribution is equal to the product of the two probabilities. So this comparison would tell us whether the two variables are indeed independent. If they are indeed independent, then we would expect that the two are the same. But if the numerator is different from the denominator, that would mean the two variables are not independent, and that helps measure the association. The sum is simply to take into consideration of all the combinations of the values of these two random variables. In our case, each random variable can choose one of the two values, 0 or 1, so we have 4 combinations here. Right? So if we look at this form of mutual information, it shows that the mutual information measures the divergence of the actual joint distribution from the expected distribution under the independence assumption. The larger this divergence is, the higher the mutual information would be. So now let's further look at what are exactly the probabilities involved in this formula of mutual information. And here I listed all the probabilities involved, and it's easy for you to verify that. Basically, we have first two probabilities corresponding to the presence or absence of each word. So for W1, we have 2 probabilities shown here. They should sum to 1 because a word can either be present or absent in the segment. And similarly for the second word, we also have 2 probabilities representing presence or absence of this word, and they sum to 1 as well. And then finally, we have a lot of joint probabilities that represent the scenarios of co-occurrences of the 2 words, and they are shown here. Right? So, and they sum to 1 because the 2 words can only have these 4 possible scenarios. Either they both occur, so in that case both variables will have a value of 1, or one of them occurs. There are 2 scenarios. In these 2 cases, one of the random variables will be equal to 1 and the other will be 0. And finally, we have the scenario when none of them occurs. So this is when the 2 variables taking a value of 0. and there's sum to 1. So these are the probabilities involved in the calculation of mutual information here. Right. Once we know how to calculate these probabilities, we can easily calculate the mutual information. It's also interesting to note that there are actually some relations or constraints among these probabilities, and we already saw 2 of them. Right. So in the previous slide, you have seen that the marginal probabilities of these words sum to 1. And we also have seen this constraint that says the 2 words can only have these 4 different scenarios of co-occurrences. But we also have some additional constraints listed in the bottom. And so, for example, this one means if we add up the probabilities that we observe the 2 words occur together and the probabilities when the first word occurs and the second word doesn't occur, we get exactly the probability that the first word is observed. In other words, when the word is observed, when the first word is observed, and there are only 2 scenarios, and depending on whether the second word is also observed. So this probability captures the first scenario when the second word actually is also observed. And this captures the second scenario when the second word is not observed. So we only see the first word. And it's easy to see the other equations also follow the same reasoning. Now these equations allow us to compute some probabilities based on other probabilities. And this can simplify the computation. So more specifically, and if we know the probability that a word is present, and in this case, right, so if we know this, and if we know the probability of presence of the second word, then we can easily compute their absence probability, right? It's very easy to use this equation to do that. And so this will take care of the computation of these probabilities of presence or absence of each word. Now let's look at their joint distribution. Right? Let's assume that we also have available the probability that they occur together. Now it's easy to see that we can actually compute all the rest of these probabilities based on these. Specifically, for example, using this equation, we can compute the probability that the first word occurred and the second word did not. Right? Because we know these probabilities in the boxes. And similarly, using this equation, we can compute the probability that we observe only the second word. Right? And then finally, this probability can be calculated by using this equation, because now this is known, and this is also known, and this is already known. Right? So this can be easily calculated. Right? So now this can be calculated. So this slide shows that we only need to know how to compute these 3 probabilities that are shown in the boxes, namely the presence of each word and the co-occurrence of both words in a segment.